Okay, let's introduce the ideas of covariance and correlation. For a single random variable, let's call it x, the PMF, px, or the PDF, f of x, provides a full description of the random behavior of this random variable, while the mean, e of x, and the variance are just statistics that provide simple but incomplete summaries of what that random variable is like. Okay, so if I look at the PMF or PDF, I get the full picture, but sometimes I just want to know something very simple, like the mean and the variance, and those are actually quite simple to also collect from data. All right, we've been looking at two random variables, so for a pair of random variables, x and y, the joint PMF, pxy, or the joint PDF, fxy, that's a full description of the random behavior of the pair, and the means, ex, ey, and the variances, variance of x and variance of y, those provide summaries of the individual random variables, but there's a disconnect here in that we have, through the joint PMF or PDF, a full description of the two variables and how they behave together, but the mean and variance are about the variables individually, and you could get them using only the marginals, and there's nothing about their joint behavior in there. So what we want is some kind of statistic that does capture the relationship between x and y. So I want a simple statistic to capture the relationship. Okay, so let's start out just by looking at something that we're going to call the cross correlation, which is the expected value of the function x times y. Okay, this captures how x and y vary together, but it also will end up depending on the individual means, e of x and e of y. And to see what that's about, let's work out an example. Okay, so in this example, I'm going to have two different joint PMFs. Okay, x and y are going to take values on 0, 1. This first joint PMF, I have a third, a sixth, and a sixth. Okay, so let's just work out what this cross correlation is going to be. So the expectation of x times y is the sum over x, the sum over y, then the function I'm interested in, which is x times y, times the joint PMF, p of xy, which I get from the table. So I have 0 times 0 times a third, plus 1 times 0 times a sixth, plus 0 times 1 times a sixth, plus 1 times 1 times a third. I just got that all from a table. That's going to end up being a third, because there's only one of those that's not 0. Okay, let's look at a slightly different joint PMF. Now the values of x and y are going to be 1, 2, and y is going to be 2, 3. Okay, so now I'm going to compute e of xy again. So I sum over x, I sum over y, x times y, joint PMF x of y, x and y. So now I'm going to get 1 times 2 times a third, plus 2 times 2 times a sixth, plus 1 times 3 times a sixth, plus 2 times 3 times a third, plus, and that's it. So we're going to say that's 4 sixths plus 4 sixths plus 3 sixths plus 2, and you can work out that that's going to be 23 over 6. Okay, so here's what happened. We computed the statistic, we got something. What's odd about this is that when I look at these two joint PMFs, it looks like they have the same kind of relationship between x and y. The only thing that's really going on is that there's a shift, okay? So x and y are shifted over in the second PMF. X is shifted over by +1 and y is shifted over by +2. But it's weird that this statistic is influenced by those shifts. So what I maybe should do is, before calculating anything, just remove or subtract off the means, and maybe I'll get something a little more useful. Okay, and that's what we're going to do. We introduce this idea called the covariance of x and y. Okay, so the covariance, which we write with the COV notation, that's going to be the expected value of x minus its mean times y minus its mean, where mu of x is the mean of x and mu of y is the mean of y. Okay, this is going to capture how the deviations of x and y from their means vary together. Okay, so before we were just seeing how x and y vary together. Now we're doing it for the mean subtracted versions, x minus its mean and y minus its mean. A useful alternative formula that's helpful in some calculations is to just recognize that this is e of xy minus e of x times e of y. Why is that true? Well, let's just quickly check. It's going to be the expectation of x minus its mean times y minus its mean. So I'm going to just expand out this product. So I'm going to x times y minus x times mu y minus mu x times y plus mu x mu y. Okay, so I just opened up that product. And now I'm going to use linearity of expectation, and I'm going to break out these terms. So I get expectation of x times y minus mu y times expectation of x minus mu x times expectation of y plus mu x mu y. That's linearity of expectation. And so now I'm just going to plug back in the fact that mu x is the mean of x and mu y is the mean of y. I'm just doing that. So I get ey times ex, ex times ey, ex times ey. And I see that I have basically three of the same terms. So I have minus, minus, and plus. So that's just going to leave with a minus. So I get exy minus ex times ey. Okay. So let's go back to this example that we looked at and just see what we should be getting with the covariance. So I already know from the previous calculation that for this joint PMF on the left, exy is a third. And on the on the right, its exy is 23 over 6. Okay, so I have that already. So why don't I use the alternative formula that the covariance of xy is equal to e of xy minus ex times ey. And that's going to be, so I need to work out the mean. So the mean of x is going to be 0 times a third plus a sixth and 1 times a sixth plus a third. So I can just read that off the table. It's going to be a half. It's simple. And it's going to get something basically the same for e of y, but let's just work it out. It's going to be 0 times a third plus a sixth plus 1 times a sixth plus a third. And that's going to be a half. Okay, and so the covariance of x and y is going to be exy, so it's a third minus a half times a half. So the product of the means, that's a 12th. What happens on the right here? Well, what's the mean of x? It's 1 times a third plus a sixth plus 2 times a sixth plus a third is equal to 3 halves. And that's going to be, for the mean of y, it's going to be a little different. It's going to be 2 times a third plus a sixth plus 3 times a sixth plus a third. And that's 5 halves. All right. So then when I go to calculate the covariance, I have the expectation of x times y, so that's 23 over 6, minus the mean of x times the mean of y, so 3 halves times 5 halves. That's going to end up being 46 minus 45 over 12, putting them all over the same denominator, and that's a 12th. So what's happened is that the covariance has successfully captured how these two joint PMFs are related, right? And the way that it's done that is by looking at how x minus its mean and y minus its mean vary together. Okay, so by removing the means, I was able to ignore the effect of this shift and just look at the configuration of the joint PMF. So the intuition that you should take away from this at a high level is that if the covariance is positive, then x minus its mean and y minus its mean tend to have the same signs, okay, more often than not. And if the covariance is negative, then x minus its mean and y minus its mean tend to have opposite signs, okay? And so you can kind of see that from the picture below. So if you think about the green region, that's where they tend to have the same signs, plus plus and minus minus. And the orange region is where they have opposite signs, minus plus or plus minus. So if the covariance is positive, it means that more of the mass tends to live, in the green region versus the orange region. And if it's negative, more of the mass tends to live in the orange region than the green region. But this is with an important caveat. So this is in a weighted average sense. And that you can see from this e of xy, meaning that larger values of x and y contribute more to the covariance. There's not really the mass in terms of probability. It's a weighted mass, and higher values of x and higher values of y tend to contribute more. Okay, so that's just a choice. We just chose to look at the covariance, and we'll be trying to justify to you as we go along in the course why this is such an important statistic. Okay, let's do an example. So in this example, I'm going to have a joint PDF. It's going to be pretty simple. It's going to be equal to a half, but its range is going to be a little bit weird. So I picked a slightly weirder range just to make this point. So either x and y are between 0 and 1, or they're between 3 and 4. So there are going to be two boxes, and you have to live in one of those boxes. Okay, and that's going to be the joint PDF, right? And so the total area of this is going to be 2, so I have to divide by half. And here's the mean. So the mean is going to be at 2, 2. So the expectation of x is 2, and the expectation of y is 2. And I can just kind of see that visually by looking at this range and taking into account the fact that things are uniform. So when I calculate the covariance, what I'm going to do is just try to use this formula directly. So that's the expectation of x minus its mean times y minus its mean. So because I'm using the idea of taking the average of a function, I can just plug in to the integral this function, which is x minus its mean times y minus its mean, times the joint PDF, dx dy. Okay? And we read off from this plot that the average should be 2, so I have x minus 2 times y minus 2 times a half, which is the joint PDF, dx dy. And I have to integrate that in split across the two boxes. So one goes from 0, 1 to 0, 1 for x and y. The other goes from 3 to 4 and 3 to 4. This works out to be 9/4. Okay, so you can kind of plug that into your favorite algorithm or work it out by hand. It turns out to be 9/4. Okay, and it's positive. That's the thing I want you to take away. It's a positive covariance. And if you think about that picture I drew on the previous slide, they do tend to live more in the bottom left and top right. And that's by design. Okay, let's do the opposite thing. Let's build an example where they tend to live or tend to have opposite signs. So we're going to use the same idea for the joint PDF, but now the boxes are going to live between, for x between 0, 1 and y between 3, 4, or x between 3, 4 and y between 0, 1 and 0 otherwise. And it's easier to see this from a drawing. So I just flip kind of the positions of these boxes. So I have one in the top left and I have one in the bottom right. Okay, so with that in mind, I'm going to have the same mean because it's a uniform height. So the mean is just going to be in the center here. So it's going to be 2, 2 again. All right, and now I can just work out the covariance. So the covariance, I'm not going to write out the abstract formula. I'm just going to write out the integrals. It goes from 3 to 4 and 0 to 1, x minus 2, y minus 2 times a half dx dy, plus integral from 0 to 1 and 3 to 4, x minus 2, y minus 2 times a half dx dy. And that's going to wind up being minus 9/4. Again, just plug it into some algorithm or work it out by hand. It's a negative covariance. Okay, so these were basically the same example, except I moved the position of these boxes, and I got that, the covariance is positive if they tend to take the same sign on average, and it's negative if they tend to take opposite signs on average. And signs are based on the sign after subtracting the means. So you have to kind of shift your frame over so that the means are at the origin. All right, let's talk about some basic properties. So the covariance has some nice properties that are useful to simplify calculations. One is that if you take the covariance of a random variable x with a constant a, you get 0, right? That's something simple. If you take the covariance of x with itself, you'll get the variance. If you take the covariance of xy, that's the same as the covariance of yx, so it's symmetric. If you're interested in the variance of x plus y, that turns out to be the variance of x plus 2 times the covariance of xy plus the variance of y. Okay, so linearity of expectation does not apply directly to the variance. You can't just write variance of x plus variance of y. you also have this covariance term. And the generic version of this is that I have the variance of ax plus by plus c. That's equal to the a squared times the variance of x plus 2ab covariance xy plus b squared variance of y. Okay, so, and the constant c is gone. So that doesn't matter because it gets removed by the subtraction of the mean. So why does this last formula make sense? And by the way, this variance x plus y is a special case of this more general formula. So why does it make sense? Well, let's just write it out. So the variance is the thing I'm interested in minus its mean squared, take the expectation. Okay, so by linearity of expectation, I can pull the constant out of this inner expectation. Okay, so, and I'm going to reorganize it. So let's just talk about this for a second. So the c's cancel. This is linearity expectation. So in the second expectation, I pulled the c out and it canceled out the first c. I pull the a out, and so now I have a term that looks like x minus its mean times a. I pull the b out, and now I have a term that looks like y minus its mean times b, and the whole thing gets squared. Okay, so now with the square, I have to do this thing where I, multiply out all the terms. So I get a squared times x minus its mean squared plus 2ab x minus its mean times y minus its mean plus b squared y minus its mean squared. Okay, and again, I'm going to use linearity expectation to pull out these constants. So I get these three terms with the a squared, the 2ab, and the b squared all pulled out. Okay, so I'm just using linearity expectation again to break this up. And I just noticed that these actually are the definitions of the variance of x, the covariance of xy, and the variance of y. And I'm done. So that's why that last formula is true. Okay, let's look at something that's also useful, a little bit more intricate. So I'm going to have the covariance of linear functions. Okay, so let's introduce a couple of new variables. So let's say I have u, which is a linear function of x and y, and v, which is also a linear function of x and y. So I mix x and y together to get u, and I also mix them maybe with different coefficients and offsets to get v. Okay, so I'm interested now to know the covariance of uv. That turns out to be ac times the variance of x plus ad plus bc times the covariance of xy plus bd times the variance of y. Okay, why this holds, and the reason I'm going to go through why this holds is it's useful sometimes to see this algebra of how to deal with covariances and variances, because it's something that can come up in some later classes. It's it helps you simplify some expressions later on. So it's just something you should see a couple of times. Let's just see why this actually holds. Okay, so the covariance of uv is just equal to the mean of u minus its mean times y minus its mean. And so I'm just going to open this up. I'm going to plug in the definition of u, which is ax plus by plus e, and the definition of v, which is cx plus dy plus f. And I get this big expression here. And now I'm going to use the linearity of expectation, and that's going to, just as before, cancel out the constants e and f, and I'm going to pull out the constants a, b, c, and d, and get all of these terms. So x minus its mean and y minus its mean are going to turn up, times a or c or b or d. That's linearity of expectation. I'm going to use linearity of expectation again, and multiplying this out to just break out these terms, which is x minus its mean squared, and the covariance term here, and y minus its mean squared. And I just recognize that what I've got is the variance of x, the covariance xy, and the variance of y times different coefficients that just fell out through this process. And that's exactly this formula I had above. A nice special case is when I just have x and y scaled, and then I have, so let's say I have a times x plus c and b times y plus d. The way that affects the covariance is I just multiply it by a times b. Okay, maybe a really simple case of that, just to keep in mind, is let's say that a is 1 and b is -1. Then the effect of this is just to multiply the covariance by -1. One more inequality I'm just going to kind of introduce is called the Cauchy-Schwarz inequality. in this case, so this has many realizations. In our case, where we're thinking about covariance, what it means is that the absolute value of the covariance cannot be larger than the square root of the product of the variances. Okay? And this holds with equality if and only if x is an affine function of y for some a not equal to 0. Okay? See your lecture notes for more details on why this is true. This is a really important and deep fact that can be really useful in kind of understanding the relationships between covariance and variance. All right, the main thing we're going to do with this idea is it lets us normalize the covariance. Okay, so now I know the maximum possible value the covariance can take. I can divide by that value and know that it will lie between -1 and +1, and that makes it a bit easier to interpret. So before, when we were calculating the covariance, I actually could have gotten any numbers between -infinity and infinity, right? So that whole range was out there. But now if I'm allowed to normalize, I just get between -1 and 1. And that's where I get this concept of the correlation coefficient, rho xy. Okay? And this is a really important idea. We're going to see this more and more. So this is between random variables x and y. I just compute the covariance and then divide by the square root of the variance of x times the variance of y. And what I know from this is that it has to lie between -1 and 1, because the Cauchy-Schwarz inequality tells me that when I divide the covariance by the square root of the product of the variances, that can have absolute value at most 1. It also turns out, so this is where this correlation coefficient is super useful, it is 1 if and only if x is a linear function of y for some positive a. It's -1 if and only if x is a linear function of y for some negative value a. Okay? So basically, this is telling you how much of a linear relationship exists between x and y, right? So if it's something less than 1, it means that a linear function does not fully explain the relationship between x and y. Okay? And let's look at something where I scale x and I scale y. Then the way that that affects the correlation coefficient is I take the sine of AB, and then I multiply by that by rho xy. And what I mean by sine here is that sine of a value z is +1 if z is positive, 0 if z is 0, and -1 if z is less than 0. I'm just introducing that here for convenience. So what it's basically saying is that the correlation coefficient is almost unaffected by linear transformation. So if I have x and y and I scale them and I add some constants, I'm still basically going to get the same correlation coefficient. It might just change. Signs. That's it. So if I take x and I multiply it by -1, then the correlation coefficient will change signs between -x and y. But that's it. It won't change its value, its absolute value. All right, let's do another example, or let's come back to this same example again. So we already know a lot about this example. I know the covariance is a 12th. I know the means are a half. And so now what I want to do is I want to calculate the correlation coefficient. Okay, maybe this is the most meaningful thing I can calculate to try to interpret what's going on between x and y. Okay, so I need to divide by the square root of the variance of x times the variance of y. And so I need to work out the variances. So the variance of x is just ex squared minus the square of the mean. This is the alternate variance formula. So the only thing I need to get is ex squared. So that's going to be 0 squared times a third plus a sixth plus 1 squared times a sixth plus a third. And that's going to be a half. And so the variance of x is going to be a half minus a half squared, because the mean also happens to be a half. And that's going to be 1/4. And we're not going to redo the calculation for y. We just know that it always ends up being the same thing in this nice example. It's also going to be a fourth by the symmetry of the distribution. And so the correlation coefficient is going to be a 12th divided by the square root of a fourth times a fourth, which is going to be 4/12. And that's going to be 1/3. Okay? Let's do the same thing on the right. Okay, so the mean of x is going to be 0 times 7 over 24 plus 5 over 24 plus 2 times 5 over 24 plus 7 over 24, that's 1. The mean of y is 1 by symmetry, right? So this is a slight, by the way, just to make this clear, this thing on the right is not the same joint PMF that was showing up before. It's slightly different in that the values of x, y are 0, 2 now, and the joint PMF values are actually different. So we're recalculating everything that we need. So we also need EXY. That's going to be 2 times 2 times 7 over 24, because all the other values are 0, so I get 7/6. So I skipped all the 0 values because they won't contribute anything. And now I can work out the covariance because I have the cross correlation and the means. So I just get 7/6 minus 1 times 1. That's a 1/6. Okay. And notice that so at this point, I want to point out that the covariance xy is larger than the covariance xy on the left, which is a 12th. So maybe I conclude that there's, like, I don't really know what to conclude. So I'm trying to compare these two random variables. What does it mean that this covariance is larger? Actually, it doesn't mean too much. It's basically kind of reflecting the fact that x and y take on larger values. So they go 0, 2 instead of 0, 1. So that's actually getting weighted in there. So it's hard to interpret, right? So that's one thing to notice. Let's go ahead and calculate the correlation coefficient. So I need EX squared. That's going to be 2 squared times 5 over 24 plus 7 over 24. That's 2, it turns out. Same thing for EY squared. It's also 2 by symmetry. And so then the variance of x, which is also equal to the variance of y, in this special case is going to be EX squared minus the square of EX. And so that's going to just be 2 minus 1 squared. It's going to be 1. That's also the variance of y. We won't redo the calculation. So the correlation coefficient is a 1/6 divided by the square root of 1 times 1, which is a 1/6. That's a smaller correlation coefficient. And on the left, I have a larger value of a 1/3. And what that does tell me is there's a stronger linear relationship between x and y. Okay, and let's go back up to the table and look at that. So if you look at the table, the times when x and y take the same value, so when they're both 0, 0 or 1, 1, that happens, each of those happens with probability 1/3. The same kind of configuration exists on the right, where I have 0, 0 and 2, 2, but it's a little less likely because it happens with 7 over 24, which is less than 8 over 24, which is a 1/3. So it's a little bit harder to capture what's going on with a linear relationship between x and y, and that's why the correlation coefficient is a little bit smaller. Okay. A couple more things. So we're going to say that x and y are uncorrelated if the covariance xy is equal to 0, or equivalently, the correlation coefficient is 0. So what does it mean when things are uncorrelated? So if x and y are uncorrelated, that means that the variance of x plus y is just the variance of x plus the variance of y, and EXY factors as EX times EY. Note that this does not buy you independence. It's just a particular factorization. And so what is true is that independence buys uncorrelatedness. And the reason why is that I can always factor the product once I have independence, and I'm taking expectations for any functions g and h. And what that means is when I go to calculate the covariance, I have x minus its mean, y minus its mean. If they're independent, I factor this function out. I get the mean minus the mean times the mean minus the mean, which is 0. The thing to remember is that uncorrelatedness does not give me independence in general, right? So you could have things that are both uncorrelated and independent, but if you only know they're uncorrelated, you can't infer that they're independent. All right. X and y, we're finally also going to say they're orthogonal if this EXY is equal to 0. And for orthogonal x and y, we have this property that the expectation of x plus y squared is just ex squared plus ey squared. That's where this idea of orthogonal comes from. And if x and y are uncorrelated, then what that's telling me is that the x minus its mean and y minus its mean happen to be orthogonal. Okay, and the reason this orthogonal term is used is that you can actually develop some geometry here using this idea as an inner product, but we're not going to go that far. But there's a way to kind of view all of this through inner products and get some geometry in this probability space. So let's do another example. So here's this pretty simple example. I'm going to have a joint PDF, which is going to be constant over a circle. Okay, so it's going to be 1 over pi, whenever x squared plus y squared are less than or equal to 1, and 0 otherwise. So that means that the range is just this filled in circle. It has radius 1. And so first of all, are x and y independent here? Well, we already have a way of quickly checking this. I know that since the range is a circle, it's not a rectangle, right? So that was kind of our first check. It's not a rectangle, it's a circle. And so that already tells me that the range will not factor out. So the whole function cannot factor out, and I don't have independence. So x and y in this case are dependent. But turns out that x and y are uncorrelated, okay? So we're going to check this. So it'll turn out that they are uncorrelated. And so the mean is 0 just by, looking at the picture. So by symmetry of x, y about 0, right? So the joint PDF is just constant. And if I stare at this range, I see that it's centered at 0 and it's, constant height. So the mean should be 0, 0. And we actually already did this in an earlier lecture. So if you really want to see this worked out explicitly, you could go back to an earlier video and see it. All right, and so let's get the covariance. So the covariance is just the expected value of x minus its mean times y minus its mean. And since these are 0 mean, I just get exy. And so I can plug into this integral. I get, I'm going to get integral from minus infinity to infinity twice, and that's going to be xy times the joint PDF times dx dy. Okay, so I just need to figure out my integration limits. I go from minus 1 to 1 for y, and the square minus square root 1 minus y squared up to 1 minus y squared square root xy 1 over pi dx dy. Okay, and so I can just work that out. I get minus 1 a half x squared from these integration limits, which are just kind of the boundaries of this circle in terms of y. And then I also have x times y, or sorry, x is already integrated out, y times 1 over pi dy. And so I just plug these in to x squared, and we can get the square root 1 minus y squared minus a half again, minus the square root squared. And because of the square, those are going to cancel out. Okay, so I don't need to proceed any further. These two terms I can just observe cancel out, and I'm just going to get 0. And so that verifies for me that x and y are uncorrelated. Right, and kind of looking at this picture, what that tells you, so one way to kind of look at it is that there's not really a good line that you could draw through this joint PDF that really captures anything. So any line is as good as any other line. So that's kind of where this uncorrelated feature is coming in. Okay, so it'll turn out, and we're going to play around with this in other spaces, that the covariance and correlation coefficient are really useful for discovering linear relationships between random variables. Okay, so that's what they're doing. You can think that the whole relationship, which could be quite complicated, is embedded in the joint PDF or the joint PMF. But if I'm only interested in what kind of linear relationship there is, all I need to do is calculate the correlation coefficient. Okay, and it'll turn out that these are in fact quite easy to calculate directly from data. So sometimes it can be very difficult to calculate or estimate the joint PDF or the joint PMF from data, but the correlation coefficient and the covariance are very easy to calculate from data. And they generalize really nicely if I have many random variables. And we're going to see how to do this with random vectors. And the one thing I want to warn you of is that they have a lot of advantages, but you should also be aware of how they fail, okay? And what I mean by that is that these are just particular statistics, and it's possible to design examples where it seems, for instance, that there's almost no linear relationship, but maybe the correlation coefficient is quite high. Or there's almost a linear relationship, but the correlation coefficient is quite low. And that's due to some outliers in the way we're thinking about it in the joint PMF or PDF. But in a data set, you could just have one or two bad points that are really changing the value that you get for the correlation coefficient or the covariance. And it's important to see some of those things visually to kind of appreciate how these statistics, while they're very useful in general, what are the ways in which they can go wrong? And those are things that you're going to see directly in lecture and discussion, right? And that is it.